This is going to be a short discussion of the hyperbolic trig functions. I want to make some comparisons between these and the regular trig functions, so bear with me while I review quickly. In a typical trig class, you have at least three ways to think about how these trig functions are defined. There's right triangles, there is a point on the terminal side of the angle, and there's the unit circle method also. The unit circle method is actually a special case of the second method, though. So on the unit circle, we can think of making an angle, the initial side of which is the positive x-axis, and the other side we'll call the terminal side. On the unit circle, for any angle that I give you, there's a point on the circle to go with it. We'll call the coordinates x and y as usual. If I tell you the angle, that tells you the point, and I'm going to define cosine of theta to be the x coordinate of that point, and sine of theta to be the y coordinate of that point. Since we're on the unit circle, it's obvious then that cosine squared theta plus sine squared of theta has to be 1, no matter what angle theta you're talking about. And then we make some definitions. We make tangent of theta, y over x, which in this case is the same thing as sine theta over cosine theta. So tangent is sine over cosine. I define the secant to be 1 over x. That would make it the reciprocal of the cosine. The cosecant is 1 over y, which is 1 over sine theta, the reciprocal. Cotangent is x divided by y instead of y divided by x. So cotangent and tangent are reciprocals of each other as well. If you start with cosine squared of theta plus sine squared of theta equals 1, you can derive two facts from that are frequently useful. In the first case, divide through by cosine squared of theta, and after you simplify it, using the fact that sine over cosine is tangent, you find out that 1 plus tangent squared of theta is secant squared of theta. And in a similar way, if you take the formula that you started with and divide it through by sine squared, you eventually find out that 1 plus cotangent squared is cosecant squared. We know that x squared plus y squared equals 1 is the unit circle. A seemingly random question is this: what does x squared minus y squared equal 1 look like? As always, the first thing I think of, I'm going to look for intercepts. Are there any places on that graph where x is 0? That would mean that 0 minus y squared would need to be 1. Negative y squared being 1, though, means that y squared would have to be negative 1. No real y number will work, so I don't have any such thing. How about y equals 0? That says that x squared is 1, and that says x could be 1 or negative 1. So this is all we know about this graph so far. No points on the y-axis, 2 points on the x-axis. People think about this in a large number of ways. I want to think about it a certain way right now, just carefully. Take x squared minus y squared equal to 1. Rearrange it to get y squared by itself. Then y is either the square root of x squared minus 1 or the negative of that. This, by the way, is why we don't see anything with x equals 0. We get imaginary y coordinates if we do this. Here's a trick. I'm going to factor an x squared out underneath the radical sign so that I can do properties of square roots. Strictly speaking, square root of x squared is absolute value of x. but I'm going to take plus and minus signs of it anyway, so it doesn't matter in this case. The y numbers are like this. Also, it's going to be of interest to me to know if I have any relative maximums or minimums in terms of the y coordinate. You may have forgotten, but there's a technique called implicit differentiation. Here, I'm going to think of x as being the independent variable, and at least locally, I'll think of y as being something that depends on x. If you take x squared minus y squared equal 1 and do the derivative of the independent variable squared with respect to independent variable is 2x, but I'm sort of thinking as y as being a function of x, so I have to use the chain rule on it. 2 times the next lower power times the derivative of y with respect to x. This side of the equation is the derivative of a constant, so that's 0. You can rearrange the algebra and you will find out that dy dx is x divided by y. We don't have any points on this graph where x is 0, so there is no way this fraction can come up 0. We do have points where x is 1 and x is negative 1. Y is 0 there, so I'm going to get vertical tangent lines there. But there's no local high or low spots. Going back to our formula, that factor square root of 1 minus 1 over x squared, if x is really large, that quantity is approximately equal to 1, and it'll be less than 1 in magnitude. So I have a point, I have another point. The tangent lines are vertical. If x is very large, either in the negative direction or positive direction, y is plus or minus x times some number that's practically equal to 1, but less than 1 in absolute value. That says when you're far away from the middle of this picture, the graph has to start looking like these dotted lines that I've drawn in, one of which is y equal x, and the other one is y equal negative x. The business about that factor being less than 1 means that all of the points on my graph are going to be within this part of the plane or within this part. There is no local high or low spots on the graph, so we literally have no wiggle room at all, and the graph has to look like this. This graph is called a hyperbola. Having said that, we're going to define two new functions. COSH, which is pronounced hyperbolic cosine of x, and SINH, hyperbolic sine of x. The e that I'm talking about here is the usual e, the 2.71 type number. I'm going to define hyperbolic cosine of a number to be e raised to that number plus e raised to the negative of that number divided by 2. The graph of such a thing kind of resembles a parabola, but it isn't one. If you do careful calculations, you find out the y coordinate on this graph gets bigger much faster than any parabola could do. Hyperbolic sine is e to the x, not plus, but minus e to the minus x over 2. Its graph roughly looks like this. It resembles in some ways y equals x cubed, but it gets steeper way faster than that. Using these two definitions for hyperbolic cosine and hyperbolic sine, I'm going to make a calculation that's seemingly drawn out of thin air, but it turns out that it isn't. I'm going to take hyperbolic cosine and I'm going to square it. I'm going to take hyperbolic sine and I'm going to square that too, but instead of adding them together, I'm going to subtract them. So I have to do my usual a plus b squared and a minus b squared routine. I get a lot of stuff here. The terms in the middle in both of these squares is 2 times e to the x times e to the minus x. E to the minus x is 1 over e to the x, so the exponentials involved are reciprocals of each other. So 2e to the x e to the minus x is really just 2 times 1, which is 2, so I start writing it that way. I have to do the subtraction and then see if this simplifies down to anything nice. So e to the 2x minus e to the 2x, that cancels out. E to the minus 2x minus e to the minus 2x also cancels out. 2 minus minus 2 sorry about that, equals 4 over 4, which is 1. So after all of this calculating, we find out we have an identity. It's kind of like a trig identity. It's kind of like cosine squared of theta plus sine squared of theta is 1, except we've got a minus sign instead of the plus. This is going to turn out to be typical of these functions. There's going to be a whole lot of interesting facts about them, and they strongly resemble the trig functions. Except instead of having the graph of a circle generate these things, these are going to be related to the graph of a hyperbola. Then we do just as we did with the trig functions. We have definitions for cosine and sine. The hyperbolic tangent is the hyperbolic sine divided by the hyperbolic cosine. The hyperbolic cotangent is hyperbolic cosine over hyperbolic sine. The hyperbolic secant is 1 over the hyperbolic cosine. The hyperbolic cosecant is 1 over hyperbolic sine of x. Just like with before, there will be identities. At the moment, I only want to look at 2 little identities. Start off with this fundamental one that we've figured out. Divide through by hyperbolic cosine squared, and you'll find out that 1 minus hyperbolic tangent squared is hyperbolic secant squared. This is just like what goes on in trigonometry, except I've got a minus sign where I had a plus sign before. If you divide through by the square of the hyperbolic sine instead, you find out that the square of the hyperbolic cotangent plus 1 is the hyperbolic cosecant squared. Since we're doing calculus, we need to know derivatives and things like that. So the derivative of the hyperbolic sine, we'll calculate this using the definition of the hyperbolic sine. The derivative of e to the x is e to the x minus the derivative of e to the negative x is e to the negative x times negative 1 because of the chain rule. That would be minus e to the x plus e to the minus x over 2. So the derivative of the hyperbolic sine function is the hyperbolic cosine function, just as it is with ordinary trig functions. The derivative of the hyperbolic cosine is calculated in exactly the same way, except previously I had a minus, now I have a plus. The derivative of e to the x is e to the x. add the derivative of e to the negative x, which is e to the negative x multiplied by -1, you'll get e to the x minus e to the minus x over 2, and that's the definition of the hyperbolic sine function. So the derivative of hyperbolic sine was hyperbolic cosine. The derivative of hyperbolic cosine, if you didn't know any better, you might think it's going to be the negative of hyperbolic sine, but that's not what happens. There's no negative sign in front of it. This is consistent with what we've seen before. These new functions will obey a variety of identities and behaviors that strongly resemble trig function behavior, but sometimes you get a plus or a minus where you weren't expecting it. Lastly, I want to calculate the derivative of the hyperbolic tangent function. It is not productive to write it in terms of the exponentials. I'm going to write it as hyperbolic sine over hyperbolic cosine, and then just use the quotient rule to calculate the derivative. So one needs the bottom times the derivative of the top minus the top times the derivative of the bottom over the square of what used to be on the bottom. The derivative of hyperbolic sine is hyperbolic cosine. So accounting for this, I'll have two factors of hyperbolic cosine minus derivative of hyperbolic cosine is hyperbolic sine, and I already had one factor of that. So now I've got two of them, and we're very happy. Hyperbolic cosine squared of x minus hyperbolic sine squared of x is 1. So I have 1 over the square of the hyperbolic cosine. That's the same thing that you would get if you squared the hyperbolic secant. So the derivative of hyperbolic tangent is hyperbolic secant squared of x. If you feel like it, you can work out the other three derivatives. Just use the quotient rule and what you know already. Don't go all the way back to the exponentials, though. So why the names? On the unit circle, x squared plus y squared is 1. And because of the way we defined the trig functions, x is cosine of t and y is sine of t, t secretly being theta for the angle. On the other hand, if you look at the graph of x squared minus y squared equals 1, this is not a circle anymore, but a hyperbola. I can think in the same way, though, if I want to represent x and y as functions of some other parameter. One way to do it would be to say x is hyperbolic cosine of t and y is hyperbolic sine of t. If I say that, then it's automatically true that x squared minus y squared is 1. So these functions are to these functions as a hyperbola is to a circle. Back in the old days, they sometimes called sine and cosine circular functions for that reason. Therefore, we ought to call these new functions hyperbolic functions. So we know what these functions are. We know how to differentiate them. We know that there are certain identities that are pretty familiar looking to us. We now know enough to do everything we're going to do in terms of these hyperbolic functions. I hope this has been useful, and I'll see you again soon.